Continuing topology of real numbers, interior of a set. In this topic, we will be covering interior point, interior of a set with the definitions and examples, and theorems and questions based upon these. Interior point of a set definition. A real number x is called an interior point of a set A if A is neighborhood of x. We have studied the definition of neighborhood. Consider a point. If open interval containing that point is contained in a set, then that set is called neighborhood of that point. And in a reverse way, we say the point is in the interior of that set A. So choose any point inside the set if the interval, open interval, however small possible, is contained in containing that point is contained in A, that means the point is in the interior. Boundary points are not interior points. However small epsilon choice you may take, the interval containing that point will be go out of the set. So boundary points are not interior points. So analytical definition, we can say the open interval with a choice of epsilon containing x is contained in A, which is a similar definition of neighborhood. And the two definitions go hand in hand. If you say the set is a neighborhood of point, in a other way we can say the point is in the interior of that set. Examples: every point of open interval is its interior point, because open interval is neighborhood of each of its points. So each and every point of open interval goes in the interior of that set. Or you can say that every point is interior point. In closed interval, if you are talking, or closed interval first A, B. A and B, which are the boundary points, are not interior points because the closed interval is neighborhood of each of its points except A and B. So A and B are not the interior points, rest all are interior points. So interval containing interior points of closed interval AB is open interval AB only. Next we have interior of a set. We have discussed interior point of a set. Now we are discussing interior of a set. Suppose there is a set. Talk about the collection of interior points it has. This is the outline of the collection of interior points. You may say only boundary points I'll be leaving in this. So this whole collection of interior points is called interior of set A. A very thin outline it may take from the set. The set of all interior points of a set A is called interior of A, and it is denoted by A0. A0 is always contained in A. By figure you can check. Although A0 is A for open set, this will be proving further later. But this is true only because clearly the definition, by the definition of open set and neighborhoods combining, we'll get this A0 is equals to A if A is open. So examples for interior of a set. If we take A as open interval AB, the interior is the whole set itself. Because AB open interval is neighborhood of each of its point and its interior is the same set itself. AB naught is AB. Naught is the notation of interior of a set. Second, for closed interval AB, A naught is open interval AB. Because closed interval is neighborhood of each of its point except the boundary. So boundary won't be there in the interior of a set. A set of real number minus infinity to infinity, it is neighborhood of each of its points. So every point is it's in the interior points. So R0 is R. Collection of all the interior point is the set itself. If you're talking about any non-empty finite set, then its interior is empty. Why? Because it is not neighborhood of any of its points. So no point of it is in the interior of the set. Hence its interior collection is totally empty. Similarly, interior collection of natural number, integers, rationals all are empty because none of them are neighborhoods of any of its points. Hence there is no interior point inside the set. Theorems on interior of a set. The very first theorem, for any set A0 is open. A0 is open. So two cases arise. If I take A be any arbitrary set, I need to prove its interior is open. Case 1, if its interior does not contain anything, A0 is empty, then it is trivially open. There is nothing to prove because phi is an open set. Case 2, if it is non-empty, it contains some elements. So let x be any arbitrary element of A0. We take any element of A0. I want to prove that A0 is open, and for open we need to prove it is neighborhood of each of its points. Because if it is neighborhood of each of its points, that simply means every point inside the set is interior point. So we have taken x any element of A0. We actually want to prove the open interval containing x, that is x minus epsilon x plus epsilon, is contained in A0. That is our aim. Now x belongs to A0. That simply means x is interior of A, which actually means A is neighborhood of x, and by applying the definition of neighborhood, open interval is contained in A, but I want to prove open interval is contained in A0. So let y be any element of this open interval, x minus epsilon x plus epsilon. And since this is an open interval, and every open interval is an open set, which means it is neighborhood of each of its points. Every open interval is an open set, and by definition of open set, it should be neighborhood of each of its points. So it should be neighborhood of y. So this interval, which is contained in A, is a neighborhood of y, which implies A is neighborhood of y, because we have studied theorem in neighborhood. Superset of neighborhood of a point is also neighborhood of that point. So by this, A is neighborhood of y. Since I have taken any point of the interval and that is in the neighborhood of, for which A has become neighborhood of that means that point y is in the interior of A. So every point of the interval is an interior point of A because I have chosen just any element and it came to be an interior point. Before this, I should say A is neighborhood of every point of this interval. So every point of this interval is the interior point of A, right? Y was any point of the interval. A became the neighborhood of y. That means you choose any point from the interval, A will become the neighborhood of the same. That means A is neighborhood of each of its points, and hence every point of the interval is an interior point of A, means that interval is contained in A interior, A0, because A0 contains all the interior points of A, and the interval is containing interior points of A. So that means interval is a subset of A0, which I wanted to prove, which proves A0 is a neighborhood of X. and since x was arbitrary, any element, so a naught is neighborhood of each of its points, and hence a naught is open. Hence proved. Next theorem, a naught is the largest open set contained in A. A naught is the largest open set contained in A. Suppose this is A and this is A naught inside A. Theorem says there is no other set in between A naught and A which is open. A naught is the largest open set contained in A. Means if B is any set that comes in between A naught and A, then B won't be open. So this is one way of understanding this. Another way I'll discuss it in a while. A naught is the largest open set contained in A. Choose any open set which is contained in A. Let B be any open set contained in A. I have assumed an open set which is contained in A. Now the another way of doing this, if B is an open set that is contained in A, then B must be contained in A naught, because the largest open set contained in A is only A naught. A naught has to be in between B and A. So B I have taken open set, also I have taken contained in A. I need to prove B is a subset of A naught. If B is empty, then B is a subset of A naught, because phi is subset of A naught. Phi is open. So there won't be anything to prove in first case. In second case, let B be non-empty. It has some elements. Let X be any element of B. I will prove X goes to A naught to prove the result. And since B is an open set, X is any element. So open set, due to open set, it should be neighborhood of each of its points. So B is neighborhood of X. But B is contained in A. That means A is neighborhood of X by the same theorem of superset of neighborhoods. Superset of neighborhood of a point is also neighborhood of that point. Any neighborhood, superset of neighborhood of point is also neighborhood of that point. So A is also neighborhood of X, and that means X is in interior of A. This means X belongs to A naught. So I have taken element X as in B. It came out to be an element of A naught, and this implies B is a subset of A naught. Hence A naught is the largest open set contained in A, because A naught is open by previous result. Every open set contained in A is a subset of A naught. You have taken an open set contained in A, it happens to be a subset of A naught. So every open set contained in A is a subset of A naught. Also A naught is open set itself by previous theorem. Therefore A naught will be the largest open set contained in A. Hence the result. Next theorem, if A is any subset of R, then A naught is a subset of A. Suppose there is A naught is always contained in A. That is very trivial with the definition of A naught, but let's see how we write. Let X be any element of A naught. See, you must remember these results now. If you want to prove a set is a subset of another set, A is a subset of B, that means take any element of first set and prove that element is present in the second set. Take X belongs to A, show that X belongs to B. By this you will be able to prove A is a subset of B, right? So consider this formulation. we need to prove here A naught is a subset of A. I'll be taking any element of A naught and I'll be proving that element belongs to A. First understand this. Now let X be any element of A naught and just apply the definition of concepts of open set, interior set, neighborhood. There is nothing else to remember. You just need to apply the understood definitions of open sets and neighborhoods. So X belongs to A naught. X is an interior of A. That simply means A is neighborhood of X. Apply the definition of neighborhood. Neighborhood means the open interval containing X will be contained in A. When the interval is contained in A, that means X is also contained in A. X belongs to A. So I have taken arbitrary element of A naught and it happens to be an element of A. That means A naught is a subset of A. Hence proved. Next result. If A is a subset of B, then A naught is subset of B naught. That is also trivial. Suppose A is contained in B in this figure. A naught will lie inside A, B naught will be inside B, little away from the boundary. So it's very visible A naught will be contained in B naught. Now let's see how we write. Take any element of A naught, prove that element in B naught. Let X belongs to A naught, X be any element of A naught. By definition of A naught, X is the interior point of A, which means A is neighborhood of X. But A is contained in B. This implies B is neighborhood of X. The same result which we have applied earlier also 2-3 times. Superset of neighborhood of a point is also neighborhood of that point. So B is also neighborhood of X. And B is neighborhood of X means X is in the interior of B, which means X belongs to B naught. Hence, I have taken element from A naught, it happens to be in B naught, that means A naught is a subset of B naught, hence proved. Next is theorem 5. A is open set if and only if A naught is equals to A or A is equals to A naught, where A is any subset of R. The result is containing the term if and only if. That means we need to prove this result both ways. First, A is open. We will be proving A naught is equals to A. Let A be an open set. We shall show that A naught is equals to A. If you want to prove two sets are equal, you need to prove each of them is a subset of other. A is subset of B, B is subset of A. This will prove A is equals to B. So we need to prove here A naught is equals to A. That means we need to prove A naught is a subset of A and A is a subset of A naught. Also, interior is always subset of A. We know it by the definition. A naught contains the interior points of A. It is trivial, right? A naught is a subset of A. To prove the other part, A subset of A naught. Now, A is an open set and A is also contained in itself. Every set is contained in itself. So I can say A is an open set contained in A, right? But A naught is the largest open set contained in A. A naught is the largest open set contained in A. This we have proved previously. So A is a subset of A naught. See, don't consider this how is this possible, how can a set be the subset of A naught. This is analytical way of telling two sets will be equal if each of them will be subset of the other. So if I am saying A is a subset of A naught, that means that is only for the case with the set is open. Consider this open interval AB naught. If I am saying AB interior is the same interval AB, that means each of them is a subset of each other. Only then the equality is possible. So combining 1 and 2, A is equals to A naught. Now conversely, let this result is true, A naught is equals to A, we will be proving A is open set. Well, we have already proved A naught is the largest open set contained in A. So A naught is open set. A naught is open set also we have proved separately in theorem 1. And A naught is equals to A. Two sets are equal, one is open, that means other has to be open too. So A is open set. So the result we have proved both ways. A is open set if and only if A naught is equals to A. Sixth theorem. For any set A, interior of A naught is equals to A naught. See, this is a compilation of two results. A is open if and only if A naught is equals to A. Right? We have just proved. Also we have proved A naught is an open set by theorem 1. So combining these two results, it is obvious if a set is open, its interior will be same. So A naught and A naught naught is equals to A naught. So compiling this here, we know this for any set A is open if and only if its interior is same. The set is equal to its interior, right? Also we know A naught is an open set. So its interior should also be same. So interior of A naught is A naught, hence proved. Next theorem, A naught is equal to the union of all the open subsets of A. Open subsets of A. See, this is set A. Suppose A has subsets, open subsets contained in A. The collection of all such open subsets means union of all such open subsets will be A naught. So we are first of all having the collection of open subsets of A. Let T be the set which contain all the open subsets of A. So these are the open subsets of A, means whenever I am talking about S, this is subset of A and S is open. These two results are there for S. And now consider a union of this collection. Union of S, S belongs to T. B is the union of all the open subsets of A. Now I need to prove this collection is A naught only. So A naught is equals to B, I have to prove this. We know A naught is an open set and it is contained in A. C S T is a collection of all the open set contained in A. That means A naught is also the part of T. That simply means A naught is a subset of B. A naught is contained in the union also, because B is the union of all such sets. Now I need to prove the reverse part. B subset of A naught I have to prove. So for this, understand this. A naught is the largest open set contained in A. And B is the union of all the open subsets of A. Since B is the union, we have also proved theorem on open sets that union of arbitrary collection of open sets is also open. We have proved this result in the open set lecture. Union of arbitrary collection of open sets is open. Since B is union of collection of open sets, that means B is also open set and B is contained in A. So B is an open set contained in A, but A naught is the largest such set which is contained in A and open. A naught is the largest open set contained in A. So this is why B should be subset of A naught. Combining 1 and 2, A naught is equals to B, which we wanted to prove. A naught is equal to the union of all open subsets of A. Hence the result. Next is questions based on the same. Find the interiors of the following sets. See, this is non-empty finite set. It is not neighborhood of any of its point. That means none of the point will work as an interior point of the set. No point is in its interior. So if I consider this set to be A, then A naught is empty. For closed interval, interior will be open interval. For this set, let this be A and its interior will contain open interval because it is neighborhood of only points lying in the open intervals. So its interior will be 0 to 1 open interval, union 3 to 5 open interval. This is the set 1, 1 by 2, 1 by 3. This is not neighborhood of any of its point. Consider just one point, 0.5. If you take any interval, there this interval will contain few points. Suppose 0.5 is the point, 0.5, 1 won't be present in the set. So this, however small epsilon you take, this open interval cannot contain the set, contained in the set. So set is not neighborhood of any of its points. Hence its interior will be empty. Integer complement. Complement of integer means r minus z. This is neighborhood of each of its points, because once you remove integers from the real numbers, it is neighborhood of each of its points. Hence its interior will be r minus z. R minus z is the set and its interior is the same. Complement of rational means r minus q. It contains irrational points. Whenever we take any point which is irrational, and this interval may contain many rational number also, so this won't be neighborhood of any of its points. See, there is a difference between non-integer and non-rational. In non-integer part, whenever I choose any point, I can get a contracted open interval which may not contain that integer. Means it's possible to find that interval. But in case of reals, where rational and irrational are so closely packed, and it is not possible to find an interval containing irrational point which does not contain any rational point. So that is why the difference. So it is not neighborhood of any of its point, hence it is not open and its interior will be empty. For the last part, where if you simplify this will be closed from 0 and open from 1, and interior will be open interval 0 to 1. So compiling in the same way as the question, it contains x such that 0 less than x less than 1.